yeah, welcome to discussion for 61C. So if you haven't been here before, this is a 2-hour section. We do usually have some sort of break in the middle. And so it's a last discussion, which just basically means it kind of lags a little bit. And if you're not fully caught up or you just want extra review, this is a good place to do it because we have 2 hours. And yeah, today we're going to be talking about RISC-V, which was covered in, I believe, the past few lectures starting from 2 weeks ago. And this past Thursday's lecture won't be covered today, so instruction format. So if you haven't caught up on that, that's totally okay. Also, it's just to check online, is the volume okay for now? Okay, cool. Yeah, so just to get started real quick, I'm going to take a skim. You can still, I think you can still see my screen sharing, I believe. Just to take a quick look over the form. It seems like most people have watched all of the RISC-V lectures, which is pretty good to see. And yeah, instruction format, totally fine. If you haven't watched it, we're not covering it today. It'll be next Monday, including call. Or actually, it might be rescheduled. Yeah, next week's lecture discussion might be rescheduled just because it's a holiday and we're technically not allowed to do discussions, but we can take a poll towards the end. And just overall, it seems like in depth, yeah, just RISC-V itself is kind of complicated. How to convert, calling convention especially. Yeah, so we're going to get to hit all of that today. Yeah, that's how we're kind of going to look at things. And as always, if you can't make it in person, the online link will always be supported. And do my best to try to like keep the two sides synced. But yeah. So just to go over some assembly basics, so RISC-V is one of the types of assembly languages that you'll see out there. You might have heard of like something like x86 it kind of is thrown around out there. That's considered technically to be a CISC language, which instead of the R, it's just a C. And that's because it's a complex kind of instruction set family and RISC is a reduced instruction set family. And the difference between that is just that like RISC is has a lot fewer instructions. If you look at the RISC-V green sheet or like any RISC-V manuals, you'll be like, oh yeah, that's so long. Like they're 50 pages, 60 pages. And then you look at the CISC instruction set manual and it's like 1,000 pages. Whoa. Yeah, Maddie over here, she's taking 152 and they use CISC there or in some RISC stuff, and you'll kind of there's a difference there. The main difference between the two besides that is like you'll notice that in RISC, like we don't have access to a lot of instructions, and so sometimes you have to do a little bit of mental gymnastics to get where you want. But every operation pretty much out there can be done with some combination of RISC instructions. In this class, we'll be using RV32, which just basically means it's the very basic set. On the green sheet that's still linked on the website, you'll be able to see like, oh, there's some FP things, so floating point things. There's also kind of certain extensions, atomics. We'll talk about that more later in the class, but for now, you don't have to really worry about them. Yeah. Let's see, what do I have? So assembly. It's the direct output of compiled code. So something that we talked about in the C section was that, okay, you do use GCC to kind of produce an executable. And then there are certain steps along the way that we kind of just bypass because normally we don't really just want to look at assembly code because it's not very useful to us. So we just go straight to the executable that we then run. I believe next lecture we'll be talking more about call, which is the series of like going from C code all the way to the executable, and assembly is one of those steps in between. In fact, it's the second step, and it's the direct output of compiling something. I think my screen is a tiny bit laggy. I'm just going to physically just slide forward. There we go. Okay, and it's also what eventually gets run. So that might be a little confusing because like, well, it's not an executable, so how can it get run? And that's just because assembly is something that can be almost always directly translated to some series of binary bits. So that's what we talked about on Thursday in translating the instructions. So that's what gives us eventually our executable after doing some more like moving things around. And that's what we talked about in call. It is also not the final form of code. So that's why I say almost always. So something in here that like might consider is like, okay, well, we have pseudo instructions, right? So pseudo instructions is the idea of basically having a nickname or a shortcut for a very common set of instructions. So a common example of that might be like, for example, if you do like add I x1 for x2. So what's happening? Wait, no, sorry. Add I x1, and then x0, x2. So basically you're adding x0 and x2 and putting the result in x1. So in other words, you're kind of like moving the contents of x2 into x1. And so because people use that enough, it got given the pseudo instruction move, which is MV. And the thing is, at the very end of the day, you can't actually directly translate move into something that the machine can understand. So then there has to be a series of like, okay, translating move to like what the actual instruction is, and then kind of decoding that. So that's why it's not the final form. Are there any questions so far? Yes.
Numbers, or can you also like add on like x2 as well?
Oh, sorry, I meant to say add. Yeah, add is just an immediate instruction. So yes, I should have said add. Sorry about that. Yeah. So the final form of code that theoretically the system would be able to understand is just RISC-V instructions without any pseudo instructions. But next week we'll be talking about like how certain things get translated. So like you might remember things like, for example, labels. That was, I think, a point of confusion during lecture. But so let me just actually do this angle. Oh wait, I realized this. I'm gonna spotlight this because I think that worked well last time. Okay, for people online, does it like show up as next to the screen sharing? Sounds good. Okay. Also to test. Yes, you can see that. So yeah, for example, you might, what was I saying? Oh gosh. I'm sorry, what was the question? Final form of code, right? Okay. So you might, oh gosh, I had a line of thought and now I've entirely forgotten what that was. Basically, the final form of code is like, okay, well, you could have a very simple like set of instructions that just kind of gets run and you can directly translate it. Oh yes, I was talking about labels. Sorry, I got there. And then so you might have things like, for example, like shell RA label. And so what this does is it jumps to wherever the label is pointing in memory. So this might be a certain section of code, and then we'll have down here like later like a label here, and then there's some code here. So let's use the previous example. We have add x1, x0, and then x2. And so what happens here is, okay, and then we have other stuff underneath here. So what happens here is, okay, we're going to jump to this label, which is some number of lines of code down from where we are currently. So let's say this is our position 1, and then this is our position 2. And then we don't know how far this is necessarily, because we could theoretically go through all the code and count it by hand, but that's not super useful because it might be like several hundred lines long. And sometimes we won't, like, we'll make a mistake. So what then happens is like, okay, well, because we can't visually do that, this eventually gets converted to some kind of memory address of sorts. So instead of like having like labels and things like and pseudo instructions, everything will eventually get converted to base instructions and some form of memory addresses. So does that make sense? Yeah.
It gets put into like the
so no, the way that JAL works, so I'll talk more about this later, but it jumps to the label and then RA is a register. And so what gets stored in here is the current position, so P1 plus 4. And the reason that the plus 4 exists is because every instruction in RV32 is 32 bits encoded or 4 bytes. So all this we'll talk about more later in some of the problem examples. Okay, and at this point, it's still human readable. So if we look at this, it's not the simplest thing to read, but we can still kind of tell what's going on, as opposed to say if you were given something that's gone through the entire process, and then now it's just a jumbled bunch of zeros and ones, and you really don't know how to interpret that because it might not necessarily be in the same order that you're looking at it anymore. And it's a set of instructions that can be directly understood by the system after maybe some minor adjustments. So these are like the minor adjustments that we're talking about, still the same concept in terms of code, but it just looks a little bit different. And then it's also built of one single operation at a time. So what this means is kind of throwing it back to lecture. if you have something like, for example, A is equal to B plus C plus D, when we're looking at this in C, like it's very obvious, like it seems like, okay, these are all kind of happening at the same time. You just kind of add on to it. So every line can like be however many nested operations that you really physically want to put in there, no matter how ugly it is. And it'll still compile and be fine. But in RISC-V, that's really not the case. In all assembly, one line is just a single operation. So if you wanted to add 3 things in assembly, you would have to do 2 of them first, and then the sum of this then gets added to the 3rd one. So each line can only do 1 thing at a time. Does that make sense?
The return address does?
Yeah. So actually keep that question. I'm going to talk about it a little bit more in I think a few slides with the registers. Yeah. And then it's even more dumb than regular computer programs. So we know that computer programs, they only do everything that we want it to do because the hardware works with the software. So at the point of assembly, we really just have to assume that the computer doesn't know anything at all and can't do anything on their own. And that's what leads to like human, I guess, created conventions, like for example, calling conventions that we'll talk about in a few slides. And so what this basically is like, if you want the computer to do something, you can't assume that it will know exactly what it needs to do. So for example, if we're going through the code right here and we're like, oh, we don't want this to happen. So we can like just assume that like it jumps over this. It really can't. Like you have to specifically redirect it, or if you don't want something to happen, you have to like write some kind of instruction to actually jump over that section of the code. Otherwise, it'll get executed. So that's something that trips a lot of people up when coding. Okay, any questions on just assembly basics? Yeah. Oh, I don't think I posted them this. Okay, let me. Okay. Sorry, I forgot to post them this week. Wait. 1 moment to do that. Oh, I didn't post them this week because I realized there's a lot of junk in the slides right now. So I'm going to update them afterwards. I'll post like what I'm working, the base set of slides, what I'm working off of right now. So, okay, as things kind of load, I will just continue talking and then, yeah, and then it's read line by line when executed, and it will only not run something when it's told explicitly not to, aka it jumps over something. Okay. Oh gosh, all my tabs went to sleep. So yeah, things are being reloaded. Okay. So next topic is generally the idea of registers. So this is something that can kind of be a little tricky to visualize, especially once we get into the CPU component of the class, because it seems like there's a lot of differences and it's like, oh, certain things are used for certain registers are used for certain things, but it's very much not the case. And that's because I think it's the 2nd bullet point. Oh yeah, okay. Well, that's just because all registers are basically the same thing. They're just a set of smaller components in the hardware that kind of get linked together, and it makes one of these. And so we know that we have 32 of them, as the next bullet point suggests. And these 32, they're all exactly the same. The only thing that changes is their inputs and outputs and how they're wired, and you'll explore more of this in the CPU project. But by themselves, we only number them because it makes it easier for us to identify which one is which, but fundamentally speaking, they are all exactly the same thing. And they're also on chip memory. So this just means that when you look at something, there is usually a chip that contains the processor as well as like other memory storage units and just like things that help, I guess, the system run. And so this also means that it's really, really fast to be able to access. And we'll see a little bit a chart of this of how different the access times is in a moment. But just know that registers are really, really fast, but because they also live on the chip and the chip cannot be huge, it also means that they're really expensive. They're all functionally the same. Oh, thank you. Yes. So yeah, if you want paper copies of the worksheet, they will sit up here, or you can pass it around. We ran out earlier, so that's why. So, okay, I guess this is a question then. What makes them different when we access and use them in assembly code? I guess I spoiled it a little bit earlier, but does anyone want to take a shot at answering it? So if they're all structurally the same and they're all basically copy paste of the same hardware, why are they, how can they be different? Is the what? Sorry. The purpose, yeah. So the purposes of them are different. They're placed in different places. So we'll see something called the reg file later, which is the register file, and it's just a big array of registers, basically. So yeah, those are all kind of touching on concepts of why they're different. And like we know, for example, like from lecture, that there are certain things that, like for example, the RA register, it's one of these that's been just given a nickname, but it specifically stores the return address. We have X0 here, which is going to be always zeros, no matter what you write to it. And so like some of them behave a little bit differently, and we know that certain registers hold specific things. Like for example, SP, it's not going to hold anything except for the stack pointer, the address of where the stack is currently. And the reason for that is just because, well, the only thing that makes them different is human conventions. We know that we want specific registers to do certain things, and we want to be able to expect the same kind of behavior across different kinds of code. So when we have that, then we need to like say, okay, well, if I expect the SP register to hold the stack pointer, we're only going to allow the SP to hold it. So even though theoretically you could write anything you want to SP and set it to whatever value you want, you actually don't want to do that, because then it messes up everything else, because all the other code is expecting SP to hold the specific type of address. Also, I just uploaded the slides, and I think my computer is frozen, at least on that browser tab. So I think it'll take a minute to register, but it should be uploaded in a minute. Okay, so the registers themselves are all 32 bits wide. And so what this also means is, well, we have things that aren't 32 bits wide. So what happens when not all 32 bits are used? So if we have something that we want to store in a register that's shorter than 32 bits, what do we do there? We sign extend. Do we ever zero extend? Maybe. Yeah. So yeah. So maybe. So yeah. That's a very fair answer, because yeah, sometimes we sign extend, sometimes we zero extend. It really depends on what you're loading in there. So what you're placing in the register can either come from memory or a separate register, or say some immediate. And so we'll see this in the instruction sheet itself. Certain things will tell us, okay, what actually gets loaded in there. And so for example, if you're loading something from memory, it's going to be sign extended, because we expect it to be stored in memory in a way that allows us to sign extend without a problem. So if it's a positive number and then with 0, if it's a negative number with 1. And you'll also hear the idea called padding. So this is, well, you heard that back in structs, and you might have heard it in number rep as well. So the difference between that and say like 0 extending, okay, I think the, oh wait, I do need to give it a name, I just realized. I call everything. Okay, it should be uploaded in the same drive that's linked on the central resources post. Sorry, it was a little bit late. And also don't be overwhelmed. It's 245 slides right now. That's also because I was shifting other things around and just decided to copy all the slides over for certain things. So yeah, we're gonna be working off of like the first small tiny chunk. I will clean them up afterwards. But yeah, so the difference, okay, I'm going to erase this real quick. So the difference between padding on numbers and sign extending is sign extending, sign or unsigned extending, sign or 0 extending. It only works when you have actual bits. So so this only works when you actually have the physical bits to sign extend into. And the reason that we actually do this is so that we can perform future operations correctly. But say if we want, we had something that we don't actually have the bits for. So for example, we want to work with, hypothetically speaking, like a 48-bit number. And inside the actual, like, we're loading it, say, from a 32-bit register. And so when we're loading it from the register, we know we only have 32 bits, but we want to like pad it to 48 for some reason, so we can convert it to a different, let's say a 12, base 12 number. So the 12 goes into 48. So in order to do that, well, we need to pad it to something. And so we give it just these extra zeros just to give it space so we can evenly divide up the bits. But the padding, they're kind of just like ghost zeros. We don't actually have the necessary bits that we need. And so that's why padding is only really used for sign conversions and things like that, as opposed to sign and zero extending, which is used for registers. Yes?
Padding go before as well.
Yeah, so it goes on the most significant bits, or the most significant bits side. Yeah. And then on the opposite side, well, what if we have more than 32 bits of data? What happens there? Yeah, so it just gets truncated. So truncated just means that certain parts are lopped off. And in RISC-V, we lop off the most significant bit side. So we only keep the lowest 32 bits of whatever data that you have. Does that make sense? Okay. And the biggest thing to remember is that anything can be stored in them, including other instructions, including just regular, what we consider regular pieces of data, ints, characters, etc. And then what's also important is memory addresses can be stored in them. And that's something that is key to remember, just because in project 2, you'll be using a function called malloc that doesn't exist in like the, obviously like as a traditional thing, but it just, like in C, it just allocates stuff on what we define to be the heap. And then you'll also use the stack pointer a lot. And the stack pointer is something that trips people up most of the time, because the stack is just viewed as memory. And so the stack pointer itself is just a position on that. So this is something I think that is really important. I think in office hours before, like it's been answered multiple times, countless times about it. So like just as a general kind of review, like we have our memory kind of set up here. Yes, I think it's visible. And say like the stack is defined to be up until here. And then lower than that is going to be like heap stuff. And so we don't really care about that. And so remember, like at the beginning of any operation or any function, stack pointer is somewhere up here. We don't really know where it is, but this is where our old stack pointer is. And what we kind of agree on as kind of like assembly programmers is that the stuff outside of the stack pointer, when you start a function, we're not going to care about it. If you try to access it by doing, like, for example, like where SP is right now, if we do something like load word into X1, actually that's a very bad idea because I think X1 is SP. Let's just do let's into a register. Let's do like X9 or something. And then we do an offset of 4 into SP. We know that we're going to load something like 4 bytes up right here. So whatever the word is right here. But this is considered bad just because we don't know what's up there. It's outside of the scope of our current function. So that's just kind of bad programming behavior, I guess. So don't do something like that. But what we can do is say, okay, well, we started this function. And now we need to like set up the stack frame. So if you remember from a few discussions ago, we talked a lot about stack frame and how the memory kind of structure changes in accordance to when a function is called versus when it's not. And so we remember something that we talked about is called a stack frame. So say we call a function dummy, and it has some number of arguments. It has some number of just variables that get created. And so it all gets kind of stored in something called the stack frame right here. And in C, we kind of took that for granted because the system took care of it. And it's because at some level, the assembly that got translated took care of that. But now that we are programming an assembly, we can't take that for granted. And so we have to do the operations that it takes to move certain things. So now we're going to physically create the stack frame and what goes on there. So first things first of what happens, well, when you do that is, well, we need to move the stack pointer down by some amount of space to save stuff onto the stack. So when you do that, we know that memory up here is high. And then we know memory down here is low. So somewhere down here is all zeros. And so if we move things down right here, are we going to be adding or subtracting to SP? Right, yeah, so we're going to be subtracting, but this is giving us more stack space. So to increase stack space, we're going to subtract it. So let's say we want to store 2 ints onto the stack. So we're going to do, what kind of instruction are we going to do if we wanted to store 2 ints onto the stack? So I guess to start, how many bytes are 2 integers in 32-bit systems? 2 integers? Huh? 8, right. So 2 integers equal 4 bytes here. So, well, we know we can't store up there because that's kind of out of our scope of focus for our functions, and we don't want to mess with anything that was already pre-saved there. So the way that we have to do it is now we have to bump it down. And because we want to store 8 bytes, then naturally we want to bump it 8 bytes down. So we're going to do something like add I, SP, -8. Are there any questions? Yes.
So we shouldn't put anything above.
Yeah. Yes. So the thing with SP is that, like, if you haven't updated it in your current scope, you shouldn't try to store things outside of there. Storing things below it before you've updated it means that, like, well, we don't have access to that space because SP marks the bottom of the current stack, so the working stack. So if you try to go anywhere lower than that, then you're going to run into memory issues. And then if you try to do anything above that before you've, like, say, updated it for your needs, like, for example, if we hadn't done this so far and we're like, okay, we're going to store 8 bytes up here, you might be overwriting stuff from, say, an outer function or previous operations that you've done. But now that we've done this, add I SP -8, what happens now is like, okay, well, we have a new place that SP is. So it bumps it down -8 bytes, and our new SP is here. So now this is our old SP, and the value of SP has changed. So now if we try to say, do what we did earlier with, so let's store some stuff onto the stack. So store word from X9 onto SP, and then store word X10 onto SP. So now if we try to store things onto the stack, it's totally okay because we've updated the stack, created a new amount of buffer space, and now said, okay, we're going to store X9 here, or the value of it, and then store the value of X10 here. So that's the difference from just going directly from where it was and going up versus giving us some space and then storing things on there. Does that answer your question?
Yeah.
Okay. I think, was there a question back there?
No, actually, no.
Okay. No worries.
Is there a specific need for that part?
Like here?
Yeah.
Oh, yeah. So, well, it's just kind of like stack that's like out of scope. I don't think, yeah, there's no real hard name for it. It's just like stuff that's not within your scope of access, basically. So like it might be things from an outer function. So the thing that just called your function, or it just might be, for example, like setting up to run actually your process. So it's just stuff that we don't really care about and we don't want to change because we aren't the owner of that. Okay, are there any questions about anything that just got written right here?
So can you quickly explain again the difference of like what adding means again?
Yeah, versus.
Add.
Oh,
So
okay.
add is just like adding something, but it takes two.
Why I started spelling add and then wrote a D. Okay. So yeah, we have add and then we have add I. And then we have also a lot of other instructions that kind of follow this pattern. And so the difference between these two is the I at the end, and that signals to us it's going to be an add immediate. So it's basically saying this is add and then this stands for immediate. And so what an immediate is just a number. When we look at it, it's very clear to us that it's like a or not a Roman, Latin, Arabic numeral. Sorry, bear with me right there. My brain just kind of went off. But it's, for example, like when we see something like that, we see that -8 is very clearly a number. If we did something, for example, add SP say X4. We don't know what's in X4. Might be a character, might be an integer, could be a memory address. So when we do something like that, we don't know that it's necessarily an immediate, so it's going to just be adding register. So you can think of this as like add R, but that looks like address. So we don't do that. So it's just the instruction by itself.
Okay. Thank you.
And yeah, this kind of thing like difference exists for a lot of different instructions as well. So you'll see it in, for example, shift left immediate, SLL versus SLLI, and the pattern continues there. Any other questions? Okay. Now that we've kind of covered a little bit of how the stack works, something else that I kind of want to talk about a little before we get on to the next part are these two instructions. Is it visible? I think it is today. So we have like store word and store word right here. Actually, wait, I'll give it a second. We can talk about it in a minute because it's literally on the next slide. So yeah, ignore me for right now. But yeah, something to note that the registers themselves are not variables. And what that means is you can't like you can set the value of the register, but it's not going to be something that you can manipulate as if it were a variable in C. So you have a limited quantity of them. You can't create more, and there's no such thing as typing. And you can only kind of take values and put values in and take values kind of out and put it somewhere else. And it's also a fixed size, 32 bits. Yes, question?
X4 is invalid.
What do you mean by invalid?
Will it return a user-generated error?
No, so what do you mean by that logic? Sorry, which logic are we talking about?
What?
Oh, because you asked by that logic. So I was
the logic that register names are not variable.
Oh, okay. So I guess what the not a variable bullet point is saying is basically just that it doesn't behave the same way as a variable, and shouldn't necessarily think of it the same thing as a variable in C because of this specifics that I just named. Like you can't change the size, you can't change the type, and there's a fixed number of them. So that's kind of the general gist of it. You can still use like the names as the names because later on we'll see next discussion and in Thursday or last Thursday's lecture, when we decode this instruction to make something that's executed, we know how to decode things like X4. Does that answer your question? Okay, cool. So just to really quickly turn your attention to the chart right there. So this was kind of taken from a set of notes that haven't been released yet. They're on caches, which won't be covered for like another 4, 5, 6 weeks. But it kind of really does give a good example of like why we care about registers and the kind of question, well, if registers are so fast, why don't we just use registers for everything? So something kind of to pay attention here is like, well, we have our on-chip components. We sort of skip the middle two right here. Because we'll talk about that in several weeks. But registers, we can see like they're the closest to the processor, and they're also very small and very speedy. So the number of cycles, so a cycle is basically a set period of time. It changes depending on the hardware that you have that we consider to be like, okay, start to end. And we talk more about this in STS, so in 2 discussions. But when we kind of take a look at it, you can think of this as like, say, half a second, for example, to kind of scale things correctly. So when we look at a register, it might take half a second to access. This next level instructions, it's slightly slower, but it's still considered to be on chip. And that takes maybe like 1 second. So it's not as fast, but it's still pretty fast. And then we have something that's kind of in between secondary memory and then kind of main memory. So this is on the like this borderline between main memory, what we usually talk about when we consider the memory kind of hierarchy here. And we can see like it quickly, really quickly deteriorates. So this kind of intermediate memory in the middle, it takes maybe 10 seconds. Main memory itself takes like 100 seconds by the scale, which is not the slowest thing in the world, but also not the fastest thing in the world. And you can see it's a stark difference to this half a second one, right? And then we have things like disk and flash memory. So this is stuff that like when you're looking at your computer spec, we have like, oh, you have DRAM of this amount of size, you have a disk space of like 2 terabytes or something really, really large. And that kind of thing is the reason that it can be really, really large is because A, it doesn't take on-chip memory, and chips are really expensive to produce in comparison. And so because it's less expensive, so we can have more of it, but it also means it doesn't have as high of like as good technology. So that's why then you have like something in the range of like tens of thousands of seconds to access. And that's stuff that, like, for example, you want to maybe like keep on back hold, like this is the last stage of memory, things that don't get accessed a lot, etc. And that's why it's also not typically used. Like we don't say, let's go access disk in our assembly code, because then it doesn't make sense because we're just waiting and waiting while we fetch that stuff. Does that make sense? Okay, and then also jumping back to registers themselves, we see a mapping here of what the different registers kind of correspond to. So this is something that you'll get really familiar with. And by the way, I think the slides are posted on the same link, so yeah. But we can see that there are nicknames for all of the register numbers, and we can see the registers numbers goes from X0 all the way to X31, so 32 registers total. And then we also notice at the bottom there are these F registers, and these are the floating point registers. They're used for the floating point extension that we don't care about in 61C right now, but just know that they exist. And if you're like, oh, well, how do we handle decimal numbers and stuff like that? It's with the floating point instructions and with the floating point registers. So for project 2, you won't be working with any floating point values, which is nice. Yes, silent cheering ensues. But yeah, you'll also notice that each of these have names because, like I said earlier, like I started using X1 and messing around with it and stuff. And then we look at here is like X1 is the RA. And so the RA itself is the return address register. And so we've specifically said this address we're setting aside to store return addresses and nothing else. It also means that, like, say if you are doing project 2 and you're like, well, I don't have any more registers. Let's use RA as just like some random registers. Don't give in to that temptation. If you feel like you've run out of registers, it typically means that you might have messed up calculations somewhere. It's like, okay, maybe I can reuse certain things. So I would adhere very closely with this, where if you have registers, you're like, I could technically use them, but they're not like for what I need, don't use them. And then we go on to, by the way, the return address, I realized that wasn't clear. There was a question in the chat about that, but the return address is just when you call a function. So with JAL A, or sorry, JAL R, that is sitting at a certain position in memory. So when we had that earlier, it was like at position 1. And then so when we return from that position, we typically want to execute the next line in a function. So like, for example, if you call a helper function, once you return from that, you want to bring yourself back to where it is. And so that's what the return address is. It tells us, okay, what's the next instruction that we want to execute? And it's the current position plus 4. And then we have X2, which is the stack pointer. So this is what we were talking about here. This moves up and down the stack. It holds a memory address, and that memory address just tells us where is the bottom of the currently active stack. You shouldn't access anything underneath that. So for example, if we have SP right here, doing something like say store word X, let's store the return address on there. Why not? Doing something like this, so store word X1 -4 SP, this is typically not considered to be good. And the reason is because usually SP is the bottom of whatever section of memory that, or of the stack that you're trying to manipulate. And so doing a -4 means either if you're doing it correctly, it's somewhere in the middle, and then you're like, okay, I'm accessing downwards, which is a bit odd. Usually you want to allocate like chunks of memory at a time of like how much you need. And then so you always like work from bottom to up to wherever you are. So that's something that could be valid, just poor convention, because it makes things confusing. Or what you could be doing is, well, this is actually the bottom of the stack, and then you're trying to access underneath that. And so that makes this invalid. Does that make sense why for like when you're working with SP, you typically don't want negative offsets?
If we're at the bottom, add SP to SP.
If you're at the bottom and then you do add ISP 8 and not -8.
Well, I mean, -8.
-8.
That's how you allocate the thoughts, right?
Yeah, so if you're at the bottom and you're like, oh gosh, I need more space for my next operation, what you would do is then, yeah, you would just allocate more space and then start from there. So it'd be like 0, 4, 8, etc. as offsets instead of like starting somewhere in the middle and then going down. And that's also a really great thing to point out, because if you realize like you're like, oh, for this one operation, part 1 and part 2, I'm like, oh shoot, I needed more stack memory, but I didn't actually allocate enough at the beginning. Instead of just continuing to go like, oh, well, I thought I needed 4 bytes, but actually I need 12 more bytes. So, and then you do your kind of 4 bytes thing. I need more stuff. So then you allocate 12 more. Instead of doing something like that, what you can do is just go back to the top of wherever you're trying to do things and then just allocate more there. So instead of doing like -4, -12, and then like negative whatever, then you just go back and say, okay, I know I need more, so I'll just do -16 all at once. So then what happens is, well, your SP is at the bottom here, and then you can just offset in order 0, 4, 8, 12. Yeah?
It might not be important, but like, we also have like access to heap. Like, how do you access heap memory?
Yeah, that's another great question. So this is the point where you realize heap memory is actually just like stuff that's defined by the system. So in C, like when we called malloc to do it, there's no implicit like function in RISC-V, because at the end of the day, there are no functions. We all define our own functions, and the only things that we have access to are the instructions themselves, which doesn't include malloc. And so in project 2, when this becomes relevant, and just for like kind of at like a nebulous kind of or abstract kind of perspective, it's something that gets defined because it uses system instructions that you'll see on the instruction, like eCall, stuff like that, to be able to request stuff from the system. And so that's all defined like in the utilities files that you'll be given. So you don't have to actually like define it yourselves, but you do have to like kind of look at the function headers and see like which argument registers take what, and then make sure you understand that. Yeah. And just as with in C, kind of the malloc function that you eventually will use, it does return a pointer. So same kind of dealing with all of that, it's just slightly in a different way. Okay, and then just going down, that was me, I just joined. Again, let me turn off the video there. No audio, sorry. There we go. Okay, so yeah, now looking at the next part, we have something called GP and then TP. So GP is the global pointer, TP is the thread pointer. Forget those two things exist. They take up space in like the memory naming convention, but we don't actually ever touch that. And I would strongly advise you from using those registers in projects and labs. And then X5 through X7, we have the first 3 of our temporary registers, so T0 through T2. So temporary registers are things that are considered to be quote unquote volatile. And we'll talk about more about this when we get to the calling convention and when we do the worksheet. But temporary registers are stuff like that you won't theoretically want to use that often again. So it might be, for example, when we had the example of like A is equal to B plus C plus D. We care about the kind of final result, which is A. And so that wants to be stored somewhere that's a little bit quote unquote more persistent. And I use quotes for all of this is because persistency, non-persistency, it's all just defined by the user and the people who are coding in RISC-V. But for example, if we do B plus C first, oh, that looks like a smiley face. If we do B plus C first, the result of this, let's say R, we don't actually care about that result. All we want to do is add result to D. And to make that really obvious to us in code, we're going to say, okay, result will go into a temporary register because it's an intermediate value. And then so the final result of here goes into a non-temporary register, which are defined as like this S registers on there, which means saved registers. And then we have, outside of that, we have our A registers. So A0 and A1 are return registers. And that just means these are registers that we can expect to hold return values. So if we have one return value, it's always going to be in A0 once we exit the function. If we have 2 return values, it's going to be in A0 and A1 respectively. And that will always be defined in the kind of function spec. And then similarly, we have argument registers, so A0 through A7. And so we have 8 arguments. If we have 1 argument, it's always going to go in A0. If we have 2, A0, A1 first, and so on and so forth. So this is all just convention. It's not like done automatically by the system. So something I'll also see that is the return addresses, or sorry, not return addresses, the return values and the argument registers, they overlap on A0 and A1. And so you might kind of say like that can be a slight issue, because if you're like, okay, well, my outer function used A1 or A0 and A1, and then we have our return values set in A0, A1. Doesn't that effectively overwrite the previous A0 and A1? And yeah, the answer is it does overwrite it. And so that's what part of like contributes to the fact of like, okay, which parts of the function save what? And because sometimes we'll want to use the argument registers later on, so we have to make sure that they're stored in a proper place before we overwrite them, say, in a different function or later on. So it might be really confusing now, but this is what the whole of calling convention kind of is taking care of. But before we get to that, are there any questions so far? Yes.
So pretty much just like something that would
Yeah. Mhm. So that's also why, like, if, like, for example, your code doesn't like behave in this way, or it like uses different things, it might not be compatible with, say, the staff provided like utilities function and stuff, because it's under the assumption that everyone's code is following the same set of rules.
So like with temporary registers, which we would want to clear them after we are done with them. Does that manually add X0 to it?
You don't actually have to clear any registers, because what happens is if you use them later, then the values, all 32 bits will be overwritten by whatever value you set later on. So you don't have to clear anything by hand unless you're trying to use like 0.
Right. Okay. So we can just like put it as an instrument.
Yeah, so basically if you like store something else in a register whose values you don't care about anymore, it just overwrites that. We'll see this in action when we start doing some of the questions on the discussion sheet. So hopefully it'll be a little more clear then. Okay. And then main memory, I'm not going to like go too much into this, but it's using the same memory mapping that we learned in C. So nothing changes at all. We saw this here. So we have stack, heap, static, and code. And then there's a review on slide 7 about that won't get to now, but it was from the C discussion a little bit 2 weeks ago. And we access it with memory addresses, same as in C. So in this case, like it might be the result of like calling malloc when you can, or it's the result of like, say, accessing the stack pointer. And it's done using like load and stores as you would with any other memory address. So for storing, which is basically going from a source register to somewhere in memory, so memory address plus whatever offset you need, it's using instructions like store word, store half, store byte, or store double. So store double is in parentheses because it's a result of being on the green sheet, so I thought I might as well put it in here. But it's actually not used in RISC-V because doubles are 64 bits, and we don't have anything that stores actually 64 bits. So yeah, I think it's just a relic of a poorly constructed green sheet from like eons ago. And then loading kind of goes in the different directions. So it goes from memory to register. So you have some base memory address in the first source address or source register. You add an offset to it. So the offset is like, for example, indexing into maybe an array or something like that. You can think of it in that way. And then you store it into a 32-bit register. And so similarly, you have load word, load half, load byte, and load double. And the direction from register to memory or memory to register is specified by the prefix, which is L or S for load or store. And the amount of data that you access at once is stored by the quote unquote postfix, which is W for word, H for half, B for byte, and then D for double. So respectively, going from left to right, it's 4 bytes, 2 bytes, 1 byte, and then 8 bytes. So this kind of harks back to our earlier discussion of what if something that we load or store is bigger or smaller than our destination. And so, for example, loads, when we take it from memory and then put it in a register, if we try to load, say, a double into a 32-bit register, we just cut it off at the 32nd bit. And we just ignore the upper 32 bits. And vice versa in the kind of opposite direction, if we say did load byte and we have a 32-bit register, or sorry, store byte, storing into the memory, if we have a 32-bit register with all 32 bits kind of filled with active data, and then we did store byte, it would only store the first byte's worth of stuff, even if the upper kind of 24 byte or bits are stuff that we care about. So it's very, very strict in that sense. So you want to make sure that you're using the correct postfix. Yes. The freeing thing? Like for memory? You do. So yes, you do. So again, like free is a label function that you'll see in project 2. And so you do actually care about memory kind of management in here, because this is even lower than C. Like C, we cared about memory management. So RISC-V, we 100% care about memory management. And so yeah, like once you malloc something, you definitely have to free it after that as well.
Okay.
Yeah. So I think once we get closer to the project, I think it's been released, but in part 2 of the project, so 2B, you'll start mallocing and freeing things. And there will almost definitely be issues kind of surrounding that, because we'll see later, but when we're calling functions and then returning from function, it kind of messes with our registers, which I'll explain in a bit. So you want to be really careful about when you're quote unquote calling functions or jumping to function labels. There is no Valgrind for RISC-V, unfortunately. So I think the main way, so there are kind of unit tests that are that 61C built to kind of help see that a little bit, but like out in the, I say out in the real world, as if any normal person is going to be programming in RISC-V all of a sudden. But say if you do end up in a position where you're doing that, there will probably be like custom tools for that kind of stuff, because memory management isn't something that's inherently built in at like this level. Yeah. And then kind of talking what I said earlier, all data will be truncated at 32 least significant bits when going when needed. And this is back what we have before. Okay, so I'm gonna, okay, yes, we have calling convention now. I'm gonna not do this slide for the time being, because we do have a worksheet to get to. Okay, so there is a RISC-V rundown, and then we have kind of stuff doing, you're talking about registers, and then we have basic instructions, and then we kind of get to converting stuff. So this worksheet itself is really, really long, so I don't think we'll get through all of the questions. So is there anything in particular that calls to everyone here? So, or is there stuff that we want to skip? How do we feel about the registers question? Skip or do? Skip? Okay, no. Yeah, so there's also printouts here if you want to do it by hand, on paper. We also have some basic instructions. So this one I'm going to just temporarily skip, because we talked a lot about, actually, wait, no. Yeah, I think for this part, we can spend maybe 3 minutes working on 3A. Or A through D rather. And so the concept of this question, let me stop my screen sharing and share on this side. Okay. I think this will work. Okay. Oh wait, no, I just stopped my screen sharing, I think. Nope. Okay. Online, can you see my screen? Excellent. Okay. Now I'm going to figure out how to share this onto the window over there. Cool. Okay, now we see the same thing. Excellent. So for this particular question, we're going to be looking at 3A through D, and right here we can see it's a snippet of code, and basically what we're asked to do is figure out what's going on here. So if you look at the code itself, it doesn't make much sense, because like, well, what's in all of these registers? So you want to actually look at the kind of problem set up here. Here. And so we have kind of a problem set up that says, okay, well, we have an array in memory that contains 7 integers, size 32 bits each. And then so we're going to assume that S1 holds the address of the element in array at index 0. So basically it's S0 is some address, or S0 is equal to or defined as array. And we know that arrays are different from pointers in the sense that like the start of it is, so array is going to be equal to ampersand array. So it holds the address of the first position, and then you're allowed to assume that the integers are 4 bytes because see definition in 32-bit systems, and our values are word aligned. So kind of recollect that a word is 4 bytes, and word aligned just means that each element starts at a multiple of 4 bytes, which makes sense here because we have an array of 4-byte integers. And then so now knowing that, what do the snippets of RISC-V code do? So assume all instructions are run one after the other in the same context, so basically in the same process. I'll keep this up and hopefully you're able to see the actual questions on your side. Sorry, I'm trying to figure out how to like keep a certain person really, really large. I think this is correct. I can't tell, to be honest. I don't know why it's flashing up there. It's a bit funky. Okay, we're gonna really quickly go over just the general process to thinking about this. And yeah, it's just for time's sake, I would give you more time, but unfortunately, yeah, we're a little bit tight today. So kind of keeping in mind everything that we know so far, we're just gonna go through each section line by line and see kind of what generally is going on. So yeah, for 2 or 3A, we only have one line to look at. It's a load word. So yeah, what do we think that this does? I heard a lot of good conversations, so I think someone probably has the answer. Yeah.
Yeah, my response is coming from a guy who basically binge did like CS170 and math 110 homework for literally a real time past week. But so not going to be the best, but I think that 3A is about the operation 3A is I think writing the memory found in the address of the element index 3 interface to register T0. More precisely, it's about writing the integer 4 to the register of T0.
Yeah, exactly. So your brain doesn't seem fried from doing all that homework, but yeah, that's exactly correct. So what we see here, just kind of breaking it down, is our base address is stored in S0 because it's the beginning of the array. And then we have an offset of 12. So this offset of 12 is telling us the index or the index of where we want to look. And we remember at like the RISC-V level or the assembly level, we can't really assume typing of any sort. So because we know we have 4-byte integers, in order to actually access or index at like index of 3, we need to have 4 bytes times whatever index that we want. So in this case, then that gives us like 3 times 4. So we know that the index itself is going to be 3. And then because this is a load where we're going from memory to register, so our destination register is T0. So we set the value of T0 to be equal to whatever is that array of. So realize this is the wrong syntax. This is the Go syntax. Are there any questions? Okay, really quickly, if anyone's confused about why this is the case, so we have our 1, 2, 3, 4, etc. And so if anyone's like, well, why is it 12 integers or 12 bytes and not 16? It's because we want the starting position of where our next thing to be read is. And so if we had like an offset of 0, it would go from the start of the array. So we would be reading from start of array to 4 bytes off from that, and that gives us 1. So then if we bump it to, okay, 0 plus 4, so it's going to bump us to the next beginning. Then that gives us, okay, the next beginning of 4 plus 4, which is 8, and that gives us 2. So when we kind of do the offset, it's the beginning of where we want to read. Okay, so then moving on to the next part, what does this do? So store word T0, 16 of S0. Yeah, so this sets, it sets array at index 4 to be equal to T0, and we know that because we have, okay, base address which hasn't changed. We usually don't want to edit our base address if it's some array that's like that we're working with or a pointer of some sort. We just want to edit the offset, and that's why we have the offset, so that we don't consistently change where the beginning of our array is. So we have an offset of 16, which is index 4. And then we're going this way from register to memory because it's a store operation. And so that means our array is going to look something like this now. Are there any questions? Okay, moving on to the next section, we see that this is a chunk of code. Any thoughts about what this does? Yeah, so in T0, it multiplies it by 4, stores it in T1, and then we do some kind of incrementation here. We load something, we add another something by 1, and then we store something. So this is a very like general, it's not exactly like what you'll see when kind of iterating through loops, but something that I will say is that this particular line indicates to us that we're doing that usually we're incrementing something. And so when we look at this, okay, we know in T0 right now, we have some value that was taken from this index. So this is a 4. So that's what's stored in T0 right now. And then we multiply that by 4. And so we're going to take that, the 4 times 4, it's going to be 16. And then we are going to add that particular thing to S0, which includes our base address. And so it's going to be, okay, array or T2 is going to be defined as array plus 16. Now, something that we do know is that this is not actually going to be index 16. It's going to be byte 16 that we're kind of starting at. And that's important because, like, again, nothing is typed, so it's not for 16 integer, it's 16 bytes. And then so the next thing that we kind of look to do is, okay, we know T0 is now some offset of 16 from the start of the array. So that's going to be index 4. So now, let's see. Okay, T2 is going to be pointing to right here in memory. And so we're going to load from an offset of 0 from that particular location. So we're going to actually load this value. So this is going to look something along the lines of, okay, T3 is equal to array plus 16 index 0. So this is very, very awful C syntax. Do not do this. But this is kind of like logically what's going on right now. And then now that we have that particular value, we're going to increment that by 1, which is what add T3, T3, 1 is going to be incrementing by 1. And then now we're going to store it back into wherever this is. So we're going to take this, and then we're going to do something like this. Let's see. Array at array plus 16 at index 0 is going to be equal to T3 plus 1. And so basically what happened was, if we kind of look back to what we were doing originally, is, well, we took the index, we took T0 and then made that our index, and then incremented whatever that was by 1 in the array. Are there any questions? Yeah, so now this would be 5 again after this step. And then our last step is, now we want to do some kind of funky XOR stuff. So now when we look at this, okay, well, we know S0 hasn't changed. So S0 still is right here. That's something important to keep in mind. We haven't updated that. If we do want to update like the start of an array, we usually want to use a different register. And so now we load the first thing from there. So that's going to be 1, and that's going to be stored at T0. So we have array at position 0, which equals 1. And then we want to take that and XOR it by all Fs. And this is something, it's kind of a little trick that you want to keep in mind. But what happens here is, sorry about all the flashing. Yeah, so we notice here that, well, okay, hex all Fs, this is 12 bits worth of Fs. So 12 bits of F, sorry, of 1, not F. And then we also know that immediates get extended. And this is because when we work with stuff like in registers of 32, like T0 here is going to be 32 bits. And we don't just have like a mystery of 20 bits that we don't know what to do with, because XORing that just doesn't make sense. So instead what happens is, when we have an immediate, because immediate instructions have 12 bits worth of immediate, we then sign extend this by 20 bits. So sign extended. And so that way we have the full 32 bits to work with. So in this case, because we have all 1s, sign extending that means that we're going to extend everything by 1. And the reason for that is because when we start with a certain number of bits, the leftmost bit is going to tell us kind of what sign it is. And so when we start with 12 bits, leftmost bit is 1. We extend all of that. And so we wind up with 32 bits worth of 1. And so can anyone tell me, like, I guess, or actually, let's go to the next line. So now that we've XORed everything by 1, so when XOR I in this case basically just means that we're going to do a bitwise XOR. And XORing just means flip all the bits logically. So once we've done that, now we're going to take the same value that we've just flipped all the bits of, and then we're going to add 1. So can anyone tell me what this kind of what all that might remind them of? Exactly. So what we just did was 2's complement. Yeah. So this is the process of turning an unsigned or positive integer into its negative equivalent and having the binary representation of that. So we take the positive version of something. So we assumed like this was positive because we looked at the integer and we're just assuming that. And then we say, okay, we want the negative version of this, or multiplying it by -1. So we want the binary representation of that to store into a register. So we flip all the bits and then add 1, and that gives us our negative T0. So this gives us T0 is equal to T0 times -1. Yes.
So excellent, all 1s. So not necessarily just one.
Yes, yes. Sorry, I seem to have missed a question from earlier, I think 3 minutes ago. What does the first line do for which section? C, okay. Yeah, sorry, I did skip over this. Sorry about that. So what happens here? So SLLI, we call it silly, and then T1, T0, 2. So what that stands for is shift left logically by an immediate. So I'm going to write that down here. So let's use a different color for this. SLLI, I think it was T1, T0, yeah. T1, T0, 2. So the C equivalent of this would be like, let's say we had a variable that was T0. So what would happen instead is T1 is going to be equal to T0 by 2, like that. And so what that just basically means is, like, say if we have, say, 1 0 1 0, if we shift it left logically by an immediate, in this case 2, what we're going to wind up with is something along the lines of 1 0 1 0 0 0. And these are the bits that we kind of added to this because we've logically shifted it. Does that answer your question? Yeah. So I guess in the whole world of shifting left and right, you can think about it as like multiplying it or subtracting, or multiplying it or dividing it by a power of 2. So in this case, when you shift it left by 2, what it actually is doing is it's going to be 1 0 1 0. Binary version. 1 0 1 0 times 4. Yes. What for this part?
Yeah.
For D. Oh, for D. Oh yeah, for D, where we sign extended was here, because our immediates in RISC-V for at least I type are all 12 bits worth. And the reason is just because when we see, like, when we talk about encoding next time, we know that we have 32 bits to work with. So if we want a 32-bit immediate, we can't just stick the whole immediate in the instruction. Otherwise, we have like no other information available. So instead, what we kind of compromise on is like, okay, I'll give you 12 bits because this is all I can afford. And then we're just going to extend after that. Yeah?
Is it all F?
Yeah, so F is the hex digit for a nibble's worth of ones. So F is equal to, or hex F is equal to binary 1 1 1 1. It's just an easier way to write it because no one wants to look at so many ones. Are there any questions? Okay. I'm going to, jump into, just given the time that we have, would you prefer that we go through a walkthrough of like converting C code to RISC-V and vice versa, or talk about calling convention? Calling convention. So it's the idea of basically how do we make sure registers stay what we expect, or how do we deal with registers changing across functions calls? That one. The other one.
From whatever Bernie doesn't want.
C1. Okay, C first. If we don't get to calling convention this time, we can always talk about it at the beginning of next one. I would just highly recommend you review calling convention before doing project 2A, because it's going to come around and bite you if you don't pay attention to it from the beginning.
Yeah.
Okay, also on mine, calling convention or C. I'll also stay behind and we can talk about C conversion. So we'll cover both, just whichever one comes first. Okay, I'm gonna just go with calling convention just because I think it's a little harder. Okay, so this part I'm just gonna write down. I have a slide for that, but it's kind of barren and I don't really like it. But the idea of calling convention, is it's also abbreviated as CC. You'll see that on your, I think, project 2 kind of spec. You'll see it abbreviated that way. Basically, this is the agreement that we have with the code and the code that has with us and us with other programmers of assembly, whoever might choose to do that, of how we handle registers. Because like we know before, system doesn't automatically just handle registers. We have to deal with everything. And that also means that we have to keep some kind of convention across all of the code that we write, that us from 3 days ago wrote, that us from a week ago wrote, and now we hate because we don't know what they were doing. So we can all basically assume those people are all entirely different programmers, and we want to make sure that things stay consistent. So calling convention kind of enforces that. It tells us, okay, well, if we call a function, say using jalr, or not jalr, like say using jal or jump or something like that, Okay, well, what can we expect to stay the same across a function, and what can we assume that has changed, and so we can't assume is necessarily the same? So something to keep in mind. We have a bunch of different registers, so the different groupings we have are the argument and return value registers. So these kind of comprise of A0, A1, and then the rest of the A, so A2 through A7. And then we have our temporary registers. Sorry, I forgot how to spell for a second. Temporary registers, and that includes T0, I believe, through T8. I may be wrong about that. Either T8 or T7. Except kind of for some reason, why is it not registering? Hello? Okay, there we go. Yeah, so we have T0 all the way through through T6, not T8. Okay. And then we have our saved registers. And this comprises of S0 all the way through S11. So we have 12 of them there. And then we have our special registers, so our return address, which is going to be RA, and then our stack pointer. That's going to be SP. And then we have our X0, or just our 0 register. And that comprises of all of the registers that we care about in 61C. So all of these you'll notice on the green sheet can be categorized into caller or callee saved registers. So what does that mean? Well, okay, when we do a function, we know that it's being called from somewhere. So in C, when we kind of look at it, we have like, oh, say we have a main function, and then we do some stuff in here, and then we call, say, like retval is equal to some dummy function, say arg0 and then arg1. And so we can take a look at this and say, okay, well, we know that the main function is calling a function, and I don't know why it's flashing so much. I am so sorry. But we know that our main function is kind of calling something else. And so we can categorize these two functions as the main function. Oh gosh. Okay, our main function being, let's see how long this lasts before I can't write anymore. Our caller, because it is the thing that is calling something, and then our dummy function is the callee. And so this is what separates it. So whatever is being called is the callee, and then whatever is calling something is the caller. And so something that you want to keep in mind is all functions, every single function out there can be considered both a caller and a callee. For example, if in the dummy function we have a dummy helper, then in that context, the dummy function is the caller, and then the dummy function helper is the callee. So we want to make sure that we obey all calling convention rules on both sides, because we can't ever say, oh, this will never be called by something else, or this will never be called, kind of a thing. So that's something to keep in mind. All functions. It's referring to the functions themselves. Like in this case, main function is the thing that calls a different function. So in this context, when we look at this, it's the caller, and then the thing that's being called is going to be the callee. And so in RISC-V, it'll look a little bit different because there'll be labels instead, but still the same kind of general idea. So the thing to take away from this is all functions should be considered caller and callee. So even if you as a programmer say, I don't think I'll ever call another function using this, you can't guarantee that, or I'll never call this function. You can't guarantee that someone else won't. So you want to make sure that every kind of code snippet that you write or every function that you write behaves as if they're both kind of thing. They're both. So how this might look in RISC-V would be like, for example, if in this case we have a main label, and then we do say like add I. Let's do this because we're fun that way. This doesn't change anything. We're just going to do this as like a dummy thing. And then we have more code right here. And at some point we do JAL, RA, dummy. And then in say another file or later down here, we have a dummy kind of label. And then we do XORI, S2, RA with X0. And then so we have some code here, and then we do JAL RA dummy function, dummy helper. And then we have a dummy helper down here. And then we don't care what it does right here. It does some stuff, and then we do jump. Okay. So this is typically like maybe some code structure that you might see. And so when we go through and kind of look at this, well, for the first one, for the main label, in that context, is main the caller or callee? Yes, it's the caller, and dummy is callee. And then if we look at the next kind of section of code, assuming this is like in a different file or something like that, is dummy caller or callee? Caller. And then dummy helper? Callee. Okay, and then we look at the last one where we have dummy helper. You can just say like, oh, at no point in time does this actually like, does this actually call any other label? And so like we can say like, okay, it's not a caller here because when we're looking at it, the code itself doesn't actually call anything else, it just returns. And so something that's important about this is, well, we're never actually going to go to another label. And so what we have here is the last line. All of these other ones have JAL RA, and so in that case, we're saving the return address into the register RA. But on dummy helper, because it's a helper function, we don't care about returning to that point. We just are gonna like close that frame after we're done. So instead, we do jump register to RA. And so what that then does is like, okay, well, if there's code down here, if there's like the next line is right here, RA is currently pointing to here. Like the value of RA, let's say RA1, that's what the value is here, RA1. So now after we kind of finish dummy helper, we're going to jump to whatever memory location that RA1 is storing. And then we're going to continue execution from there. At some point in the future, we probably are going to have return from the dummy function. And so we'll have JRRA there. And that RA is going to be a different value because at that point, we're going to just say this RA is going to be RA2. And RA2 is pointing to right here, return address from our outer function. And so when we call that, then we're going to jump back to that location and continue execution from there. But there's a really glaring kind of issue right here. Like, how do we have multiple RAs? How many people are kind of confused about that? Excellent, great. So the reason that that exists or that's possible is because of calling convention. We know that we only have one RA kind of variable, register, etc. And we want to make as good use of it as possible, but we only have one of them. So we can't really do anything else with it but say, okay, well, every time I have a new RA, I'm going to overwrite the old RA. But if we just overwrite the old RA without saving it somewhere, it also means that we no longer have access to where we wanted to return in past functions. So effectively, if we just overwrote RA right here and didn't do anything, then it just means we can't ever return back to the blue section with RA2, which kind of becomes an issue. And so that's why we have calling convention. So this along with other reasons. So if we go back to the calling convention section here, we're going to start labeling some of these. Can everyone tell that this is a different color? Okay. So we're going to start labeling some of these with being caller saved versus callee saved. And I'll explain what that means in a minute. So argument and return values. Just kind of guessing we have a 50% shot here. Do you think it's caller or callee saved? And that basically means, does the caller save it before we call the function? Or does the callee save it after we've called, when we're inside the new function? But take your best shot. It's totally fine if it's caller saved. Caller saved. Okay. Oops. There. Are there any kind of rationales as to why it's caller saved? Any less personal reasons? Okay, so if you're not sure why, that's totally fine. You might remember earlier when we talked about the whole idea of like, well, what if we want to reuse the arguments after we've called the function? By that point, A0 and A1 have already been overwritten by the return values in A0 and A1. So we don't want to put it on, and we know that like A0 and A1 have to be set to the return values, and then as soon as they're set, then we want to return, and we don't want to reset those to something else. So kind of functionally speaking, it doesn't really make sense for the callee to save it because we want A0 and A1 to be maintained as the return value values. So we don't want to like kind of recover them to the argument afterwards. So instead what happens is we're going to have the caller save it. So say if we wanted to access certain arguments after we've called the function, I'm going to zoom out a little. So if we wanted to access whatever arguments main took in after we called dummy and dummy returned something, then we want to do, before we do JAL RA dummy, we want to save the argument registers somewhere. And any guesses as to where that might be? So what's somewhere in memory that we can easily manipulate? I think I heard a whisper of what was the correct answer. Yeah, okay, the stack. Great. So yeah, the stack, that's why it's so valuable at this point to understand how the stack works. And that's why we talked about it for like straight 20 minutes earlier, because everything that's kind of temporary goes onto the stack. And that makes sense when we think about when we talked about it in the C section, because, well, we didn't actually do anything to the stack. The system took care of it, but the system was taking care of it because the assembly code that it got compiled to took care of that. So, and that's why we cared about that. And so what happens here is, okay, well, that means at some point before before we called this, we're going to use this color. Cool, it registers. So instead what happens, let's say A0 and A1 are two arguments into main. So once we have that, say we want to use it again. We're going to use A0 and A1 after this. So use A0, A1. I don't care how, we just know that we want to use it. So instead, what we can do is we can do like, okay, well, we're going to add I, SP, -4, or sorry, not -4, -8, because 2 registers. And then we're going to save whatever it is that we want to save onto the stack. So this section takes care of saving our arguments. So now, even if A0 and A1 both get overwritten by whatever return value comes from dummy, so we don't actually care because we know at this point it's been safely stored on the stack. And because we have the agreement here that, well, if inside a function, we won't actually touch anything outside of that function's kind of stack frame, we know that that'll be preserved. Obviously, you can be malicious and say, I'm just going to change whatever I want on the stack just because I feel like it. And that's just violating kind of assembly convention. So you can assume that won't happen unless for some reason you write that into your code. Does that make sense so far?
So by putting it on the stack, that means like it's saved when we call dummy.
Yeah.
Like A1 and A0.
Yeah, so the values got saved on the stack. The registers themselves don't get saved on the stack. It's the values inside. So we basically copied it from the register and put it on the stack. So you can think of it as like X9, X10 right here. Okay, and so now let's say, okay, well, this has, let's say dummy has 1 return value. So retval goes into A0. And so once we return here, we can say, okay, well, if we want to copy this to some other argument, let's say, we're going to do move. Let's move it into the first saved register. So now this moved our return value A0 stored in A0 into S0. And so we know that by like calling dummy and making it have a return address or a return value, we know that it consequently like overwrote this A0. But what if we do something like, for example, load word A0 0 SP. Does that restore what's needed to be restored? So assuming this is all our code, if we use A0 and A1 after that line that we just wrote, is everything good? Sure. We have one sure. Any other thoughts? I shrug. Yeah. So visually speaking, this looks entirely fine, but we can't actually assume that this is okay. And the reason is because not just registers that have return values might overwrite the A registers. We have to assume any register that falls under that general category will be overwritten over the course of a function. So if we like use A0 and A1 after this line, we can't assume A1 hasn't been changed. We have to assume it's been changed even if it hasn't by dummy. And so if you do something like this, it then violates calling convention because in our eyes, A1 was never set by main after we called this function. And so therefore to us, it's a garbage value.
Wait, I'm very confused.
Yeah, no worries.
Wait, like, so we created like the A0 and the A1 like above like the dummy thing, and then you're saying we can't access the A0, A1?
So okay, so what happened here? What happened here is we're taking our A0 and A1 arguments for main and storing onto the stack where it's safe.
Yeah.
But once we call dummy, we have to assume that A0 and A1 both have been changed, even if there's no return value for either of them. And the reason for that is because it falls under like the quote unquote volatile registers, which just means assume across any function call, these registers will be changed. And so afterwards, if you want to use either of them, you have to kind of reload them from off of the stack and then restore the stack, or you have to set them to a new value. Otherwise, the calling convention checker for project 2 or just overall, it'll kind of be mad at you because in its eyes, after calling dummy, you don't know what these two registers hold. And so if you use them, it's kind of like using an uninitialized variable in C. You don't know what it holds, even if it's correct.
Oh, so like you can get them from the stack.
Exactly.
Oh,
So that's what we're doing with this line. We loaded A0 off of this, or the value of A0 off of the stack where we saved it previously, but we have to also do a load WA1 from position 4 on the stack in order for it to work. And then after that, we have, sorry, I ran out of space, but after that, we have to restore the stack before we want to use it again, because at this point, we've gotten both of the values that we want off of the stack. So that position is no longer necessary. So we restore the stack with this instruction. Does that make sense? It is a lot. Yeah, for sure. I'll stay behind a little bit to answer any questions. I'm just going to, especially for this, I'm just going to go through the other ones really quickly just for the sake of time. But if you have any questions later, feel free to ask. And yeah. And also on the discussion thread, I believe for this, you can always ask questions to that, or just on Piazza overall. But yeah, for temporary registers, I'm just going to categorize them. Temporary registers are also caller saved. So like what we saw earlier, it has to be saved outside of when we called the function itself. Saved registers are callee saved. And I'll demonstrate that in a second. Return address is caller saved. The stack pointer is callee saved. And X0 doesn't have anything because X0 never changes. So, okay, what does it mean to be callee saved? We saw what it meant to be caller saved. It meant we have to store them to the stack or do something with it that makes sure we can like re-access it afterwards. But for it to be callee saved, it's going to be slightly different. I'm going to actually just duplicate this page just because I want to delete some stuff. How do I paste it is the question. I don't actually know how to do that. Okay, I'm just gonna like select everything and then move it to a new page because I want to delete that stuff at the bottom for space, but I also don't want to delete it overall. Okay.
Wait, will this also be in the resource?
Yeah, I'll upload this after discussion. So I'm gonna just erase this stuff at the bottom. And we're just gonna assume that this was declared somewhere, but we don't really care because space. So, okay. Okay, So we're going to draw this line right here and just say that everything after this is what we care about. Oh gosh, it crossed out dummy. Okay, so what does it mean to be caller saved? So we know that the stack pointer and the saved registers are going to be callee saved. So what that means is they get preserved, their value gets preserved across a function call. So this also means that as a caller, you don't have to worry about the stack pointer not being what you're expecting it to be, and same with the saved registers. So we saw that the A registers and similarly the T registers across a function call will not be preserved, aka you have to reset it afterwards to use it. But that doesn't occur with the stack pointer or the saved registers. So how do we actually do that? Well, let's say we're using S0 and S1 in this particular section for dummy. So what you have to do is, well, before doing anything else, you want to make sure that you save certain things onto the stack. We want to make sure that we save whatever saved registers that we use back onto the stack. So here we know we are going to use S0 and S1 later on, so we're going to bump the stack down. So add I SP SP -8, and then we're going to just store these values onto the stack. So this helps us maintain, so say S0 and S1 were saved outside of the function or were used outside of the function. We don't know if they were used. We also don't care if they were used. We just know that as we're writing the dummy function, we are going to use these and they will therefore be changed. So now we're going to do whatever we want it is inside of here. We might change S0, we might change S1, we don't know. And then afterwards, after we're done computing everything and we're ready to return from the function dummy back to main, what we want to do is basically do the opposite of what we just did here. So we want to load the old values of S0 and S1 off of the stack, so back into S1 and S0. And then we want to restore the stack by doing add I SP SP8. So what we see we've done here is, okay, we've saved the values of S0 and S1 and we've restored them later on. So once we do return here, we know that they'll be the same as when they started because no one has touched the stack illegally, assuming that's the case. And then something else is we notice that we also restore the stack. Remember that SP is just a register value. So if we bump it down by a certain amount, we have to bump it back up by that certain amount. So basically like those stack operations are going to be bookended. If you bump the stack down at some point, later on, when you're done with that particular section of the stack, you have to add it back up. So that's how what maintains SP up here.
Is that like kind of
like what?
If you're bumping it back out, it's a little bit like free.
Sort of, yeah, like freeing the stack in that sense and restoring it. So what this is typically called is this is called the prologue of a code. And then you'll see this in the pseudocode or like the comments of project 2. And this is called the epilogue. And so this is what bookends all of the operations that happen inside any certain piece of code. Bookend just means you start out with one thing and then you have to have the opposing thing to after you're done with everything. So you can think of it as like open parentheses. Like if you have a certain number of open parentheses, you have to have that number of closing parentheses in the same order. So inside out, basically. So like theoretically, this is kind of getting a little complicated, but if inside like here you bump the stack down again, like say 20. This happens someplace inside here that we don't really care about. At some point before here, you have to bump it back up. So you have to do the opposing action here. And this is after you're done with the stack at that point. So you can't like say, take this and like do it after this. Oh, my battery is also running low. Excellent. Okay. So if you like put this down here, it's not going to work because they mismatch. You're going to run into issues because, well, we bumped it down by 8 and then we bumped it down by 20, but now we raise it by 8, save some stuff, and then bump it up by 20. In total, it's the same amount of memory, but it's bad because we've like messed up the order. So if it's 8 and then 20, it has to be 20 and then 8 and not the other way around. Does that make sense?
So we should have added the 12 before this.
Exactly. Yeah, you need to add it before. So any outside action has to come after, like the opposing outside action has to come after the inside actions, like a set of parentheses. Sorry, I'm looking for an outlet before my computer completely dies. Over here. Right there. Oh, right. Okay. Oh, yes. I forgot these existed. I could have prevented this. But yeah, so that's kind of the gist of calling convention. It's basically none of the reason that it exists is because we can't guarantee what registers we change or don't change within any certain function. And so we have to make sure that things that we want to use later after we return from a function have to be preserved. And so we've just said, okay, well, T registers are going to be preserved before we call the function. S registers are going to be preserved within the function that we call. And so this is the agreement that we have. So any function that you write needs to have an epilogue and a prologue and epilogue. But if it doesn't call any function inside, then you don't need to worry about the caller side because it's not a caller.
So should the reading thing from priority though?
Yeah, so this needs to happen, say some stuff happens inside here. It needs to like, basically it's like, okay, if you have a square bracket and then like a parentheses and then a squiggly bracket and then a parentheses, you need to like pair it back up by doing this, right? And you can't like mismatch them. So I'm just gonna like finish it off. This will be in the recording, so if you have to head out, feel free. I'm gonna stop screen sharing here, but just gonna show something real quick on the slides. I can screen share again. There we go. Okay. So what happens here is, okay, calling convention. You don't want to save all. Oh gosh, I just realized it completely died. Hold on. I think that actually won't work. I just screen shared on Zoom. But basically what happens is you don't want to save all your registers onto the stack by default because that's poor coding convention, and it also like makes the stack all bloated for no reason. And you also want to make sure that when you're bumping things down, you're bumping it down by 4 times the number of registers that you're saving because each register is 4 bytes. When you're doing the prologue, aka saving things onto the stack, you're using save word. And then if once you're done with that, you want to use load word to kind of load it off. That's the kind of general gist. The notes on RISC-V, I think, have a more comprehensive overview of like exactly what you do. So. Cool. Okay, we ran a bit over time. I'm going to stop this recording right now, but if you have any questions, feel free to drop them in chat or ask them in person.